Welcome to the Crazy Hat Chemist. So another video here on acids, bases, and titrations. Bam! So we're talking about an introduction to pH today. Here we go. So pH stands for the presence of hydrogen in solution. So pH is the expression of the acidity or the concentration of hydrogen ions in an aqueous solution. pH is the negative logarithm of the hydrogen ion concentration or hydronium ion concentration in moles per liter. Okay, so here's that equation mathematically. pH is equal to negative log, the brackets mean concentration in moles per liter of the hydronium ion. Now remember, again, we already talked about the similarity and difference of hydrogen ion and hydronium ion. Many times textbooks do the shorthand notation of a hydrogen ion, but they really mean hydronium ion when it's in an aqueous solution. So you need to be thinking of hydronium ion. That's what it really is. Okay, here's a little diagram of the pH scale and some things about it. So on the far left-hand side, you should see that it's red because red is the litmus paper color for an acid. And the right-hand side is blue, where the blue is the color of the litmus paper when it's a base, and neutral is that green region in between. Okay, this is a logarithmic scale, as the pH equals negative log hydronium ion concentration implies, certainly. So it's like the Richter scale, where every 1 in pH, every increase or decrease, so pH 7 to pH 8 is actually a 10-fold increase. Every 2 pH values is a 100-fold increase, etc. Okay? So some things to point out here. On the far left-hand side, you should see HCl in that little bottle in the red. That's why the acids typically have a red cap on the bottle, because they are acids. They turn litmus red. That's why it's red. And I let you know already before what the strong acids are, and hydrochloric acid, or HCl, is one of those. You should see Coca-Cola is the next thing. That is also an acid. Coca-Cola has a pH of around 3 approximately, so it's very acidic. That's not very good for you and your body. There's wine that's also acidic. Okay, mineral water, when it's carbonated water, is also acidic. Blood is approximately neutral in pH, so that for our body is neutral in pH approximately. That's pH 7. Okay, soaps, with the addition of a base, a strong base, and fats, okay, is a base, and that's why soaps are slippery, and that's why they do so many wonderful things. And this is going towards the basic side here, past the neutrality side. Okay, dishwashing detergent, laundry soap, and oven cleaner, all those things are in the basic region. And then on the far right-hand side of this is a strong base, and that is lye, which is sodium hydroxide. All right, so in the middle here is neutral, and neutral means that the pH is 7. When neutral, you have the hydrogen ion, or hydronium ion, is equal to the hydroxide ion. Therefore, they are both equal to 1 times 10 to the negative 7. Okay, so if I do the pH is equal to negative log of hydronium ion concentration, and I know the hydronium ion concentration is 1 times 10 to the negative 7. If I plug that into there, what is the pH that I get? 7.00. Now I'm going to let you know about one other thing here. There is a rule dealing with logs and natural logs, and the rule in significant figures dealing with logs is that you will end up having 2 decimal places at the end. So every single time that you give a pH or a pOH value, then you're going to have 2 decimal places in the pH value. That is 7.00. It's not just 7. Okay, on the far left-hand side where it's acidic, the pH is going to be less than 7. That means any pH is less than 7, that is acidic. The hydrogen ion concentration, therefore, will be greater than 1.0 times 10 to the negative 7. On the far right-hand side where it's basic, the pH will be greater than 7, and therefore the hydrogen or hydronium ion concentration will, of course, be less than 1.0 times 10 to the negative 7. Okay, So you got neutrality right in the middle, and you got acidic, which is less than pH of 7, basic, which is greater than pH of 7. Okay, here's a couple more diagrams to help you out. Here's another diagram here, and this is just a vertical one here. You can have a pH of 0 and you can have a pH of 14. So effectively, the lowest pH you can have is 0, and that would be battery acid, all those strong acids that I mentioned before. Okay, we have stomach lining acid, which is hydrochloric acid in your stomach. You got lemon juice, vinegar, then you have grapefruit juice, orange juice, sodas, tomato juice, acid rain, that we already talked about acid rain, okay, soft drinking water, okay, black coffee, urine and saliva is about pH 6. Then we have pure water that is without any ions in solution, and that's pH 7. We have seawater, which is pH 8. Okay, notice that urine, saliva, and seawater are all very close together in that pH of 7 range by a factor of 10, but they're very close. Then getting more basic, we have baking soda. Okay, that's why baking soda is used as a neutralization reaction. If you spill an acid in the lab, then you pour some baking soda over it to neutralize it. Okay, then we have milk of magnesia, and that's to help if you have an acid indigestion in your stomach, then you're going to drink some milk of magnesia, which is magnesium hydroxide. Okay, then you have ammonia solution, so that is a weak base, just like acetic acid or vinegar is a weak acid. We have soapy water, which we're using soap to clean our hands and wash our body. We have bleach and oven cleaner. These are very basic. And we have a drain cleaner, okay, which is very basic. Here's another little scale here for you. It's showing some of the same things, but it's just on a different scale here, just different look to it, but it's the same thing. Remember that in the middle is pH 7, that is neutral. When the pH is less than 7, it's an acid. When the pH is greater than 7, it's a base. Okay, here's some equations for calculations of acid-base calculations. These are essential. In fact, what you need to do is you need to memorize everything that is on this slide. You're going to highlight this slide and say, I need to memorize everything on here. If you memorize everything on here and know how to use the math equations and manipulate them back and forth, because there's a lot of similarities and a few differences, you will be really well set off for this unit here. So the first one is the pH is equal to the negative log of the hydrogen ion or hydronium ion concentration. And the hydronium ion concentration is equal to 10 to the negative pH. Notice that these are opposite features of each other, like addition, subtraction, multiplication, division. Okay, so you can toggle back and forth essentially between the pH and the hydronium ion concentration. Just as you have the POH is equal to negative log of the hydroxide ion concentration, and its counter of hydroxide ion concentration is equal to 10 to the negative POH. Okay, the Kw, which is the constant for water, the products over reactants, stoichiometric coefficients as exponents, the ion product constant of water, which is the Kw, that is the product of the hydronium ion concentration in moles per liter times the hydroxide ion concentration in moles per liter, and this equals 1.0 times 10 to the negative 14. This is at 25 degrees Celsius. Okay, the pH plus the POH is equal to 14. I want you to notice that there's a similarity between these two equations that are written in white on this screen here, right? Because if you take the negative log of the 1.0 times 10 to the negative 14, which is the Kw, you're going to get the 14 right there. Okay, and negative log of hydrogen or hydronium ion concentration is pH. Negative log of hydroxide ion concentration is POH. So therefore, the sum of those two is going to equal 14. Okay, the Kw, which is the ion product constant of water, which is equal to, at 25 degrees Celsius, of 1.0 times 10 to the negative 14. That is equal to the Ka times the Kb. Okay, so if we ever have given the Ka value and we want to solve for the Kb value, we can do that. And conversely, with the Ka or the Kb. Okay, then we're going to be using this here concept that we talked about in the equilibrium unit, and that is if 100 times the K, and we're going to call this Ka, Kb, Keq, doesn't really matter, but if 100 times the K is less than the initial concentration, then we're going to use the approximation. That means that we don't need to use the quadratic equation. Okay, so you need to memorize all the equations on this one slide here. This is the foundation of this entire unit on acids, bases, and we're going to be using this on every single titration problem. You need to be able to manipulate these equations back and forth. You need to be able to solve for these equations and then just flip them around, use them, turn them upside down. They will be your friend if you know them. Okay, here's a little bit of acid humor here to break it up. Okay, Ferris Nicholas was an alchemist. Ferris is no more. What Ferris thought was H2O was really H2SO4. So, hopefully you know that H2SO4, that's in red because, of course, that is a strong acid. And again, that is the only multiprotic strong acid that is sulfuric acid. Okay, it's only the first hydrogen that is important. Okay, the second hydrogen, now it's not a strong acid anymore. Okay, I am the Crazy Hat Chemist, and of course I am the wizard of all chemistry. So that's why you're going to give me a thumbs up. That's why you're going to subscribe to my YouTube channel and find my cool website online. We'll see you next time for more cool chemistry videos and solving of some problems, and I'll see you next time. Bye for now.